Today what I want to present is a comprehensive project that I call the Vega project, or Vegan, that we are pursuing at Leiden Observatory. And the goal, Albert, youth. And the goal of this project is to deliver unique constraints on the galactic center, complementary to what we can do directly observing the galactic center, and at the same time constrain the galactic potential using hypervelocity stars, but also in combination with other galactic tracers like streams, for instance. And just let me remind you the current sample of hypervelocity stars. We know of roughly 20 stars that are nominally unbound from the galaxy, observed in the outer halo at distance greater than 50 kiloparsec with velocity greater than 350 kilometers per second, and an equal amount of stars that are bound, but they may be sharing the same origin that we call bound hypervelocity stars. Okay. So this comprehensive project lies on 4 pillars. Modeling of ejection mechanisms, acquiring data, in particular from the GAIA catalog. Yeah, maybe I should have mentioned that why I'm doing this now, because of the possibility to acquire a much larger, less biased sample of hypervelocity stars and other tracers, thanks to GAIA data releases that are coming online soon. So the 4 pillars are modeling ejection mechanism, acquire more data, a larger and less biased sample, exploit this data, so modeling data for science exploitation, and also capitalizing on all this work, we would like to combine the information from hypervelocity stars with information from other galactic tracers in a consistent statistical framework. So basically what is being routinely done in far-field cosmology to constrain the cosmological parameters, we want to do it here for the first time in the near-field cosmology. Okay, and we have started with Stella this year, so this is early days, so I have no results to show. So this is done for this pillar. I will show you results next time that we meet. But this is quite exciting. Technically, it's I like it. But before continuing in explaining the other 3 pillars and show you some results of what have we done so far, I have promised to a bunch of you that I would reveal here the true but mysterious acronym of the project. As a matter of fact, the Vega project should have been called with an acronym that I think would have been memorable. But I was told slightly unprofessional, and but I like it very much, so I'm really revealing this now. So light and dark in GAIA galaxy. Okay, so I think you would have remembered that better than Vega. Okay, so moving on, the first pillar, modeling ejection mechanisms. So in a series of papers with Rem and Shio Kobayashi, and now also with Alberto, we have been actually building a theoretical framework to precisely model the Hills mechanism, so the tidal disruption of a binaries by supermassive black hole, but also the ejection of stars, hypervelocity stars, from slingshot effect, the talk that Alberto delivered yesterday. Why efficient? So this framework allow us, of course, to build, to efficiently explore the parameter space so that we can build a data analysis pipeline for data. And also allow us to build mock GAIA catalogs that we are using in a variety of ways, and this paper is today on the archive. And one way we use these mock data is to forecasting the sample that we will be able to collect in the GAIA data releases. So for the final data release, we will have what I call a golden sample, so of the order of 250 hypervelocity stars, for which GAIA will give us directly 3D velocity and position with an exquisite accuracy. So for instance, the proper motion will be constrained better than at 1% level, and parallax is better than with a relative error smaller than 0.2, and which is that makes life easier if you want to go from parallaxes to distance. But the overall sample that we hope to collect is of thousands hypervelocity stars with proper motion error less than 10%. So the horizon, relative horizon of these two samples is 20 kiloparsec, so the inner halo, and going out to 40 and 50 kiloparsec with less precise sample. So the outer, also the outer halo, so very exciting. And what about the masses? So the most of the stars will be of one solar masses, so different from the Warden-Brown sample. But the golden sample, the one with three-dimensional velocity, will have mean mass of 3 solar masses. Okay, so but I didn't want only to do theory. I wanted to acquire more data. So for the golden sample, for these 250 hypervelocity stars, what we are doing is to develop an efficient analysis pipeline for computing the distance using, of course, a Bayesian approach, calculating the total velocity, taking into account carefully the correlation of the errors, and of course, and trying to efficiently do the tracing back of the orbit so that we can statistically tell you where they're likely coming from. Okay, but for the majority of the sample, we won't have the radial velocity from GAIA. So we need to find hypervelocity stars in a reduced parameter space of proper motion and parallaxes and position. And hypervelocity stars are rare, so we expect one hypervelocity star in every million normal star. So we need to differentiate these stars in this reduced parameter space from normal stars. So what we have been done in the last 2 years is developing a GAIA data mining algorithm based on machine learning. We found that this was extremely efficient in finding hypervelocity stars. I'm missing the right word. But this, find the hypervelocity stars, but of course these are hypervelocity star candidates. And for confirmation, this has to be complemented with a follow-up observation program. So I'm getting more and more involved into observation and, for instance, into weave. And we actually have already applied this strategy to the first GAIA data releases successfully. And let me tell you a little bit more about this. Okay, so I said that we use a machine learning algorithm, so we are feeding the algorithm we have been given using our mock catalogs, examples of hypervelocity stars in every position in the sky. For instance, hypervelocity star, which is, I'm the sun. So a hypervelocity star which is nearby is a high proper motion star, but a hypervelocity star which is far away is a high radial velocity star. So the appearance of hypervelocity star changes according to its position. And so we have been given example to the algorithm. So we have been trained the algorithm and validated so that it could then subsequently find hypervelocity stars. In particular, we have chosen a neural network because among the algorithm that we tried, a neural network is great in handling unbalanced sampling, so finding rare objects. Just for calibration, when a data scientist tells you, oh, this is an unbalanced sampling, they are talking about 10 to the minus 2, 10 to the minus 3. I'm talking about an imbalance of 10 to the minus 6. So we had to develop, we are pushing this to the extreme. At least for the paper that we published, right now our neural network is a simple binary classifier. How does it work? We feed the algorithm for each star with its proper motion, parallaxes, and position. And then the function whose parameter had been fixed by the training is giving an output which is a number between 0 and 1. 0 would be like not in hypervelocity stars. 1, yes, it's in hypervelocity stars, and a number in between for, I mean, since I'm not a computer scientist, let me call it a probability, okay, to be a hypervelocity star. Okay, so we have so the very 5 minutes after the first the GAIA data release was published, we directly applied this algorithm to the mode of the parameters, automatic parameters of each star. And I was very nervous. What if my mock catalog would, be complete anchored to observation, would give completely random results. Okay, so we applied this, and this is what we found. That was a big, because if you see, this is the number of stars, and this is the probability. So at least the algorithm found that most stars are normal stars. And hypervelocity stars is just like a very small fraction, 1%. So this was very reassuring, at least number-wise. So single-handed, we could exclude 99% of the catalog and go down to 1%, which represents only a sample of 22,000 stars. Then we did a quality cut, and then for each stars, we constructed the probability distribution of being performing 10 to the 5 realization of the astrometric parameters of each star. We could construct the probability distribution, and then we took only the stars that have a mean minus sigma greater than 0.9. This was our best sample. Okay, but those stars had only proper motions, so we had to acquire radial velocities. So we cross-check with available radial velocity surveys, especially the RAVE survey, and then I wrote my first observational proposal to the INT. Actually was a director discretionary time. Well, I just wrote an email and say, please, give us the time. And anyway, we obtained the time at the INT in La Palma, and we obtained the spectra of other 22 stars. So we had a total of 47 stars with three-dimensional velocities. Okay, now the next big test for our data mining routine, find what if we find extremely boring, slow-moving stars? Okay. The good news was that 45 stars were 1 sigma outlier with respect to the halo velocity distribution. 14 stars had the total velocity greater than 400 kilometers per second. And 5 out of 14 stars have probability greater than 0.5 to be unbound from the galaxy. And this is summarized the result after we do the tracing back. So what we found is 5 stars, the yellow ones, which had, you know, large velocity between 400 and 700 kilometers per second, but that cannot be traced back to the galactic center at 3 sigma or more confidence level. So these are our runaway stars, we think. Instead, 6 stars cannot be traced back. So, sorry?
The others can be traced back?
So 5 or 6 are consistent with coming from the galactic center in a statistical way, given the uncertainty on the astrometric parameters. Yes, and we call it hypervelocity star candidate. Okay, at the level of this data release, I wouldn't bet my career on this being true hypervelocity stars, but let's assume they are. Let's assume they are. I can tell something about, you know, let's assume they come from the galactic center. So these are the hypervelocity star candidates, and for this, for 4, we could acquire the spectrum. So that's what we want. That's just an example of the kind of science we want to do. And what we found is that there are low metallicity stars, and there are 1 solar mass stars, around 1 solar mass stars. Okay, so that might be very interesting. One thing, that they are very fast stars, and also their trajectory are very eccentric. So they have their eccentricity larger than 0.9 something. Okay, so if they are halo stars, they are high velocity radial stars. But okay, I'll tell you more. We will go back to this when in the second GAIA data release. We have better constraints on that. So stay tuned. Okay. Now, so this is what we are doing to acquire more data, and they are keep implementing and improving the algorithm. But we want also to exploit hypervelocity star data. So what we have done with the current sample is to model the current sample in the context of the Hills mechanism. This is a paper in collaboration with REM as well. And we found a very interesting constraint for the binary population that I want to show in a minute, just to flash them. But this was really proof of principle that this kind of modeling can give joint constraints between the galactic center and the galactic potential. Okay. So this is not a fit. It's just to visually tells you what that you know, this is a model, and this is the current sample. And since there aren't any stars observed with velocity greater than 700, and there is no obvious observational bias, why is that? In order to fit this data, you need an extremely steep high velocity tail, like v to the minus 7 or so. And this gives strong constraint to the binary mass ratio and separation distributions, because the high velocity tails is mainly sensitive to that. Okay, so what you're looking at is this parameter space, so mass ratio distribution for the binary. This is a constraint for the binary in the galactic center. So that's how I see it. And this is binary separation distribution. Okay. By comparison, I put here in this white part of the parameter space observed parameter space, for instance, in the galaxy, this up here, or in the Large Magellanic Cloud. Okay. And this stripe here is the locus of models that fit better the current sample. As you see, although there are some overlapping with the distribution observed in the Large Magellanic Cloud, the best fit is for steeper distribution. For instance, or I need a semi-major axis distribution which is increasing, so more wide binaries than tight binaries, or I need mass ratio distributions that are steep negatively, which means that the hypervelocity stars has that we observe had preferentially a companion of low mass. Okay, so the next theoretical questions, what we are trying to do this, is understand whether this discrepancy can be due actually to the dynamical mechanism that takes these native distributions and turn into these distributions. So the dynamical effect that feed the tidal sphere of the black hole. They may modify the distribution. And so we are hoping that understanding this mismatch, we can learn something about the dynamical processes in the galactic center. Okay. And of course, what we want to understand though, and this is led by Omar Contigiani, another PhD student of mine at Leiden, is how better we can give this sort of constraints with GAIA data. Okay, so we are forecasting the ability of GAIA data to constrain the galactic center and the galactic potential parameters. And also another interesting thing, and we are trying also to feed our data mining routine. So he's trying to understand which stars bears most of the information so that we concentrate our search on certain type of stars. And this I talked already about, and so I'm just living with my dream team +1.